This video illustrates how confidence intervals for distribution parameters can be created if there's only a single experimental condition. The data being used is the same as before. It's the counts data of scores in a classroom, and the data has already been read into the ILLMO program. So one way of obtaining information is to select the histogram characteristics and to get some basic information about the histogram, which is the red curve that has been read. So one of the things that we obtain is that the average is 3.1, standard deviation is 1.41, and so on. ILLMO approximates this histogram by the Gaussian distribution, which is the green curve, and the parameters of that distribution, which are the average and the standard deviation, are specified here. But we notice that the average being used of 3.14 is slightly different from the average for the histogram, as is the case for the standard deviation, and this is partly because the Thurston modeling that we use also takes into account the discrete nature of the data. One of the pieces of information being provided by traditional statistics is said that the average is 3.1 and the 95% confidence interval for that average is 2.44 till 3.76, which means that there's a 95% probability that the true average, the population average, is actually in between these two values. And this confidence interval is used to make statistical inferences, like for instance, if you had the hypothesis that the average was 3.5, it turns out to be within this confidence interval. That hypothesis cannot be rejected based on the data. If your hypothesis was that the average was 4, that hypothesis can be rejected. But it's pretty obscure, certainly to novice users, where that confidence interval comes from. Now, traditional statistics is very much relies on Gaussian distributions, and the confidence interval is actually determined based on some analytical results that are known from theory. ILLMO has a different approach, and we will show how confidence intervals can be created in ILLMO for the same case. We go to the probability dialog and to examine PDF parameters. So what we see is again that this average of 3.147 that we saw before is being shown here. But below it, there's a possibility to create what is called an LLP, a log likelihood profile, for instance, for the average. The log likelihood profile is the red curve, and it shows how the log likelihood criterion increases if the average value is not equal to its optimal value, but to a value which is higher or lower. As the optimal value is 3.14, the log likelihood profile is 0, and since it's an optimal, it means that the log likelihood profile has to increase on both sides. And there's a very general theorem in statistics that says if you intersect this curve at the chi-square value with 1 degree of freedom, which is 3.84, you get the 95% confidence interval, at least a very close approximation to it. And that confidence interval is mentioned here, and you see that it's almost identical to what we found before using traditional methods. Now, there's a number of advantages. This result works under the assumption that the data is actually discrete and not continuous, as was for the original statistics. But another advantage is that it's not restricted to creating confidence intervals only for averages, but for any parameter. So you can also create the log likelihood profile for the standard deviation. And we see that there's a confidence interval. And so if the assumption was that, or the hypothesis was that the standard deviation was 1, you see that it's just outside the confidence interval, so that hypothesis can be rejected with 95% confidence. Another very interesting parameter or statistic to look at is actually the ratio of the average over the standard deviation, which is called the average effect. And so just as easily as we have calculated the confidence intervals for the other parameters, we can also find the confidence interval for that parameter. Now let's go back and look, for instance, at the standard deviation and create a log likelihood profile again. So we saw that one was outside the confidence interval if we had 95% confidence. Now we can change that percentage to, for instance, a higher value of 99%. If we now recalculate the log likelihood profile, we found exactly the same profile, but the intersection is now being done at a higher value, which means that the confidence interval becomes bigger. And in that case, we see that 1 is just within the interval, so that means we cannot reject the hypothesis that the standard deviation is 1 with a confidence of 99.